Today's lesson is on significant digits, also called significant figures. This can be kind of a tough topic, but don't worry, we're going to do lots of practice problems. Okay, we're going to spend the first couple of weeks working with these. What significant digits allow you to do is to accurately round your answers to calculations. And we'll be doing a lot of calculations there in our physics units. So I'm going to start by giving you an example. The example is I want to find the volume of the demonstration bench. So I need to measure it. I have my meter stick. First, measure the length. And it is 2.45 meters long. Measure the height. Okay. 0.925 meters tall. And I measure the width as 0.77 meters wide. So formula, length times width times height, I multiply them together. So I multiply them on the calculator, I have it here, and it is 1.745012.5. Okay? Unit label, meters cubed. Okay, cubic meters. Okay, that's my volume. That seems pretty accurate. I have it to the 10th place, 100th place, 1000th place, 10,000th, 100,000th, millionth place, the 10 millionth place. So I am accurate to the 10 millionth of a cubic meter. Wow, I'm pretty good. But no, really, I'm not that good. How accurate am I? There's no way I'm that accurate. All I used was this meter stick. That measures in millimeters. There's no way that my volume is accurate to the 10 millionth of a cubic meter. What significant digits allows us to do is to round this to show how accurate I really was. Now, am I going to round it to 1.745013 or 1.745? Maybe I get rid of all of these. You know, how do I round this? I said significant digits is going to show us how to round it. Before I show you the rules for that, I'm going to do one last example to again show you how this idea of significant digits falls. You can only be as accurate as your measuring stick. Okay? I can't be as accurate to the 10 millionths of a cubic meter because my measuring stick wasn't that accurate. Okay? And so my last example is football. I'm a huge football fan, especially Green Bay Packers fan. So let's say the Packers are driving down the field, running back is tackled a few inches from the goal line, 4th down. So 4th and inches from the goal line. They do a quarterback sneak, give it to Aaron Rodgers, and he runs into the end zone. Touchdown, Green Bay wins, yay! Okay. He ran it in from inches. On the stat sheet, though, for his rushing yardage, what do they give him? Do they just write down inches? No. They write down yard. They give Aaron Rodgers 1 yard, even though he only ran the ball this far. Okay. They couldn't give him a statistic in inches because the football field is measured in yards. That's what their measuring stick is in, so that's what they had to give. Okay, that's that idea of significant digits. Okay, you can only be as accurate as what you measured with. Okay. There are 4 rules to figure out what digits are significant, and then some rules to apply them to adding and subtracting, and rules to apply them to multiplying and dividing. And that's what I'll show you next. Go through the rules really quickly, and I'll show you a little trick to make it maybe a little bit easier, and we'll go through some examples of calculating with significant digits or significant figures. So first, let's go over the rules, and I'll try to go through these fairly quickly because we are going to do lots and lots of examples of these when we get to class tomorrow. So there are 4 rules for significant figures, significant digits. First rule, digits from 1 through 9 are always significant. So for example, the number 34 has 2 digits. Neither the 3 or the 4 are zeros, so it has 2 significant digits. How about 1578, so 1578? Well, it has 4 digits that aren't 0, so it has 4 significant digits. Pretty simple. Okay, the first rule is very simple. Second rule is also very simple. Zeros between 2 other significant digits are always significant. So if the zeros are between 2 numbers that count, then those zeros will count as well. So for example, 304. The 3 and the 4 obviously count because of the first rule. It's a digit 1 through 9. The 0 is now between the 3 and the 4, so it counts. So this one has 3 significant digits. All 3 of them count. How about 3004? Are these zeros between 2 digits that count? Yes, they're between the 3 and the 4 that count, so you have to count both of those. So this one has 4 digits. How about the number 3.04? Is that 0 between 2 digits that count? Yes, again, the 3 and the 4 count because they're numbers 1 through 9, so you have to count all of those. So there are 3 digits for that one. Okay, so the second rule is pretty simple too. Third rule, getting a little more complicated, but it's not too bad. 1 or more additional zeros to the right of both the decimal place and another significant digit are significant. The zeros have to be to the right of the decimal place and to the right of another digit to be significant. So, 3.30. Is that 0 to the right of the decimal place? Yes. Is that 0 to the right of a number? Yes, the 3. So that counts. So there are 3 significant digits there. How about the number 20? Is the 0 to the right of the decimal place? No. Is it to the right of a number? Yes. But it's not to the right of the decimal place, so it doesn't count. So the number 20 only has 1 significant digit. See kind of how that works? How about the number 3.400? So is this first 0, is that to the right of the decimal place? Yes. Is it to the right of a number? The 4, yes. So it counts. Is this 0 to the right of the decimal place? Yes. Is it to the right of a number that counts? Yes, the 0 and the 4. So that one has 4. Okay. Now the last one is again a little bit trickier. Zeros used for solely spacing the decimal point, the placeholders, are not significant. So if the only reason that the 0 is there is to show you where the decimal point is, then you can't count that 0 as being significant. And it fits with the other rules too. So let's do an example of 0.07. So look at the third rule here. Is that 0 to the right of the decimal place? Yes. Is it to the right of a number? No. There is not a number here. So it's not to the right of a number. It's just to the right of the decimal place. It is just a placeholder. So it does not count. There's only 1 significant digit here. The only reason that 0 is there is to tell you that that number is 7/100ths. It's not 7/10ths. Okay, that's why that 0 is there. That 0 isn't actually a number. It's just a placeholder telling you that this is 7/100ths, not 7/10ths. So that 0 did not count. How about the number 300? Again, we look at kind of that third rule. Is that 0 to the right of a number that's significant? Yes, the 3. Is it to the right of the decimal place? No. So it doesn't count. How about this 0? Does it count? No. Same thing. To the right of a number, the significant number, but not to the right decimal place. So those zeros, those are just telling you that it's 300-ish, essentially. It's not exactly 300 maybe, but it's somewhere right near 300. Now, like I said, that one is kind of confusing maybe. We'll see some more examples coming up. Now, next slide is going to show you a little trick that, that some people have done that will help out. And this is kind of the Pacific or Atlantic trick. So if the decimal is present, okay, so decimal present, count from the Pacific. Decimal absent, count from the Atlantic. So you look at this number here, 31.80. It has a decimal present, so go from the Pacific and stop once you hit a non-zero number. Okay, so stop once you hit a non-zero number. You obviously hit the 3 right away. It's a non-zero number. So then everything else counts. So 31.80 will have 4 significant digits. Does it fit the rules that I just told you? Yes, that 0 is to the right of a number and to the right of the decimal place. So it fits the rules, and that kind of the trick works. Same one here, a decimal is present, so go from the Pacific. So keep going until you hit a non-zero number. So you've crossed through all those zeros. It means all those zeros don't count. That 0 over to the right of the 2 does count because you stopped once you hit the non-zero number. So this one has 2 significant digits. Again, you think about the rules that I taught you. These zeros are to the right of the decimal place, but they're not to the right of a number. There's no number here. Okay, so it works with the rules that I taught you too. These numbers, so decimal absent. If there isn't a decimal, then come from the Atlantic. And again, stop once you hit a non-zero number. So you go through the 0, you hit the 3. That means the 0 doesn't count. So you have 1, 2, 3, 4 significant digits. That 0 was just a placeholder. Same thing here, go from the Atlantic. You cross through all of those zeros. They don't count. So you're only left with 1 significant digit in this. So it's a nice little trick that does work. So like I said, the rules are what are behind it, the rules that we learned here, but the trick does work. So let's do a few more examples. You can think of that trick that I just showed you or think of the rules. Either way, we're just going to go through some examples really quickly. How about 30.70? The 3 and the 7 obviously count because they're non-zero numbers. This 0, does it count? Yes, it's between 2 that count. Does this 0 count? Well, is it to the right of a number? Yes. Is it to the right of the decimal? Yes. So it counts. So we have 4. Oops. 4. If you think of the Atlantic Pacific trick, the decimal is present, so you go until you hit a number, which was a 3, and stop. Oh, all 4 do count. Again, so that Atlantic Pacific trick works, or just following the rules work. Okay, number 301, the 0 is between 2 that count, so it gives us 3. 480, the 0 is to the right of a number, but it's not to the right of the decimal, so it doesn't count, so that would be 2. And if you think of your Atlantic trick, you're coming from this way because their decimal is absent, so you come from the Atlantic, and you end up crossing through that 0, and you're only left with the 48, the 2. 400, I don't know what happened there. All right, here we go, we're back. 480, oops, let's do 480.1. Again, the 0 is between, so it counts, so that'll be all 4. So hopefully you're getting the idea. Let's try 480.0 and 480.00. What about those two? Again, whether you're doing the Pacific trick, you're coming, the decimal's present, so come from the Pacific on both of them, and you'll stop right away. So it must mean that there are 4 there, which there are. The 0 is between 2 that count. That 0 counts because it's to the right of the decimal into the number. It means there's 5 here. Does it really matter? Like, is there a difference between 480.0 and 480.00? Is that different? Yes, they're more accurate. This one is accurate to the hundredths place. Well, this one's only accurate to the tenths place. So yes, those are 2 different numbers, even though it seems like, oh, they're the same number. Oh no, they actually are different numbers because it's a more accurate number. You've measured exactly to the hundredths place. Or in this one, you didn't. Maybe your ruler wasn't quite that accurate. Okay, so that's kind of going over the rules. Now that we have the rules, we get to really kind of the importance of these things. And the importance is that we can use them when we're calculating. So it says when multiplying or dividing, round your answer to as many significant digits as the multiplied or divided measurement showing the least number. So when we're multiplying or dividing, I'll show you the addition and subtraction rule next, we're going to round based on significant digits. So we're starting with the multiplying and dividing. So you're going to round your answer to as many significant digits as the multiplied or divided measurement showing the least number. So in simple terms, go back to your problem, find the significant digits, and round to that many available. Let's do some examples. 14 times 3 is 42. How many significant digits does 14 have? 2. How many does 3 have? 1. So it says round to the least number. 1 is the least number. So my answer can only have one significant digit. So I'm going to round 42 to 40. Okay, I need one digit, so I'm going to start with the most left one, and then I look to the next one here, and I see, is that 2 going to make the 4 go up to a 5 or keep it a 4? And it's because it's less than 5 itself, it keeps it a 4. So I have my 40 as my answer. I like to think of this like money. Let's say that somebody owes me $42. And I say, let's just round it to $40 to make it even. That's what we're doing. We're just rounding. And we have to put that 0 as a placeholder. If somebody owed me $42, I wouldn't say, let's just round it to $4. That wouldn't make any sense. You have to put that 0 there as a placeholder. Let's do another one. Now let's do 14 times 13. How about? So 14 times 13 is 182. Look back at the problem. 14 has 2 digits. 13 has 2 digits. So my answer can have 2 digits, the number of the least. So 182. So again, I need 2 digits. So I'm going to put my 1 and my 8. Or start with that at least. And we'll look to this one. Look to the 2. Is that going to make the 8 stay an 8 or round it to a 9? It's going to stay an 8 because the 2 is less than 5. And now I have to fill in a 0 with that. Again, if somebody owes me $182, I'm not going to round it to $18. I'm going to round it to $180. How about 140 times 0.6? That is 84. 140, how many digits does it have? Significant ones, it has 2 significant. 0.6 has 1 significant. So how many can my answer have? Just 1. So 84, again, somebody owes me $84. We're going to round that to $80. You start with the first one, and then look to the next one and see where it rounds. How about, let's do 21 times 32.0. That's going to be 67.2. Look back, 21 has 2, 32.0 has 3, the zeros to the right of the decimal, and the number counts. So my answer can only have 2, so 67.2. So I'm going to put my 6 there. My 7, does it stay a 7 or does it become an 8? It stays a 7 because I look to that too. And there we go, 67. It has 2 digits. Can I put 67.0? Can I do 67.0? No, because then that 0 would be to the right of the decimal and it would count. So I have to leave it just at 67. Another one, real quick, 0.08 times 19 gives me 1.52. 0.08 has how many? 1 only. 19 is 2. Because remember, the 0 is to the right of the decimal, but not to a number. So it means I have to round 1.52 to only one significant digit. So I look at that 1, and I look to the next number. Okay, that 5. Oops. Is the 5 going to make that 1 round up to a 2 or stay a 1? It's going to round it up to a 2. So someone owes me $1.52. I'm going to say, let's round it to $2. Again, I think making it sound like money makes it work just a little bit easier. So it works for multiplying, dividing. It also works for if we want to do a dividing problem, we can. Let's do about 24 divided by 18, which gives us 1.333 repeating. Obviously, we know that's not significant because with it repeating, so we're just going to round that to 2 digits because they both have 2. So that'd be 1.3 rounded to 2 digits. So that's the multiplying and dividing rule. That's the one that we are going to use most often in class. Okay, we're going to use that kind of almost every day in our physics units. The next rule, adding and subtracting, we are not going to use this one very much. I want to teach it to you because it's one of the rules, but we're not going to use it very much. It's a completely different rule. When adding or subtracting, round your answer to as many decimal places as the measurement having the fewest number of decimal places. So we're not doing significant digits anymore, so it's an easier rule because we're using decimal places, not significant digits. So let's just do, how about we do 2 examples only, real quick. 32.5 plus 14.82 plus 3.5. Add those up and we get 50.82. Now I look at decimal places. That one has 1 decimal place, 2 after the decimal place, 1 after the decimal place. So my answer can only have, as the same as the fewest, so my answer can only have 1 after the decimal place. So 50.82 will round to 50.8. Okay, only 1 after the decimal place. About 48 minus 32.4. Subtract that, we get 15.6. Again, look at after the decimal place. How many does 48 have after the decimal place? 0. That one has 1. So obviously my answer can have 0 after the decimal place. Uh-oh. So I have to get rid of that. Can I just round 15.6 to 15? No, that 6 is going to round the 15 up to 16. And there we go, no decimal places. So there's my answer. Like I said, we're not going to be using this adding and subtracting rule very often, but it's a pretty easy one when we do, and I'll remind you, of course, of it when we do it. So let's go back really quickly to the problem that I had here with the demonstration bench. And my numbers, if you remember, they were 2.45 meters long by 0.925 meters by 0.77 meters. And I multiplied that out, and I got this horrible number of 1.745012 meters cubed. And again, we know that I'm not nearly that accurate to whatever 100,000th place that is, because I just put the meter stick up there. So what can I round it to? Now that we know our significant digits rule, we look up. 2.45 has 3 significant digits. 0.925 has 3. 0.77 has 2 significant digits. So my answer can have as many as the fewest, so that'd be 2. So I'm going to round this to 1.7 meters cubed. That sounds like a much more reasonable number than that really long number. My demonstration bench is 1.7 meters cubed volume. Makes a lot more sense. Like I said, if you are a little bit confused and a little bit lost, I'm going to have some worksheets. I'm going to put you with partners, and you are going to do lots of examples to practice these, and you'll understand it. It is confusing if it's the first time, but you'll get to practice, and you'll figure it out, and I'll help you. Thank you.